All right, so welcome to part 2 of the Learn pymatgen series. In the previous part, we talked about structures and molecules and went over those objects in great detail. Today, we'll be talking about how you can turn those structures into density functional theory calculations with VASP. We'll talk about how pymatgen allows you to automatically write VASP input files. And then we'll also talk about how once you've run the calculation, pymatgen can be used to parse those output files and give you useful information and plots from your calculation. So let's just get started. As I mentioned, we're going to be going over making VASP inputs and parsing VASP outputs. If you don't know what a pymatgen structure is, definitely go see part 1 of the tutorial. If you don't know what VASP or density functional theory is, this probably isn't a tutorial for you. You should probably just go watch something else altogether. But with that, let's just go and start. So the first thing I'm going to do is just make sure I have pymatgen installed by importing it. And I'm using version 2024.6.10. I'm also going to define just a quick helper function for printing files because we'll be writing like INCAR and kpoints files out. I just want to be able to print them in the notebook so you can see what types of information was generated. So we'll define the helper function, import pymatgen, and we're ready to go. So the first thing we're going to talk about is how to write in VASP input files manually. So this is going to be like the least useful part of it because we're going to have to tell pymatgen everything that we want to write essentially. And so this is basically pymatgen taking the information and then writing the files for us. But later on in the tutorial, we're going to talk about automatic VASP input file generation, and that's going to be much more useful, I think. And just as a refresher, the 4 input files that we're trying to create for VASP are the INCAR, kpoints, POTCAR, and POTCAR, and you should be familiar with that already. Okay, now one thing that we need to do before we go ahead and start writing input files with pymatgen is to set up our POTCAR directory. So VASP doesn't allow distribution of the POTCAR files, which contain the pseudopotential information. So there are instructions about how to set up the POTCAR files for pymatgen at this link. Just follow those instructions to set up the POTCAR generation process. Basically what you have to do is to download the POTCAR files from VASP. That'll give you a directory like this directory here. And then you run a couple of pymatgen command line functions to configure pymatgen to use those POTCAR directories. And ideally, if there's multiple POTCARs that are shipped with VASP, you will configure all of them because that will allow you to use all the different functionals available to you in VASP. Once you've gone ahead and done that, you can run the following code snippet, and that will confirm that you have the POTCARs installed correctly. So let's go run this. And because I've already run the configuration, it tells me that my POTCAR setup is correct, and it begins printing the POTCAR for these 2 elements. Now, this iron PV corresponds to which iron pseudopotential I want to use, so it corresponds to this tag here. And this functional PBE54 tells me which of the POTCAR directories to use for which functional for this POTCAR. In particular, it's going to use this PBE.54 directory when I choose the functional as PBE54. There are other options for this functional, and you can see a list of them printed out here. All right, so now that we've gone ahead and set up our POTCAR directory, I'm just going to create a test structure. You should be very familiar with this from part 1 of the tutorial. And then this test structure is going to be used to generate the inputs going forward. So my test structure is just going to be like a basic sodium chloride structure, 2 atoms, nothing very fancy in here. One thing to note, however, is this structure.sort line. Structure.sort function does is it just makes sure that all the elements of the same type are grouped together in the structure, so you don't like alternate sodium, chlorine, etc. This just makes the POTCAR file much better later on. So here's my structure file. Let's go ahead and start creating some VASP input files for this. Okay, so to begin, we're going to be writing the INCAR file. Now, pymatgen has a class called INCAR in pymatgen.io.vasp. If you want to use it manually, you have to specify all of the tags in the INCAR that you want to use. And then the INCAR object will then be able to write the INCAR file. So if we were to run this, for example, this will write a file called INCAR. And then if you print out what that file looks like, this is a helper function that reads the INCAR file and prints the first 10 lines. And we can see that the tags that were written in our INCAR file are going to be the same as the tags that we defined. So pymatgen is not really doing a lot here, just writing a file with the information you gave it as a dictionary. If we look at the next manual creation, we can look at POTCAR files. And here pymatgen can help you a little bit because once you've defined your crystal structure object, you can just directly write that to the POTCAR format using the POTCAR object in pymatgen. So here we can see that we now have this structure written out in a POTCAR format, and the corresponding file was also written to our directory where we to check it. All right, the third file that we'll talk about is the kpoints file, and there are many different ways to initialize the kpoints file in pymatgen automatically. We're not going to talk about all the different ways to initialize a kpoint file manually just because we're going to talk more about automatic generation later. But you can, explicitly give kpoints. You can use one of the automatic modes of VASP, which is what we're doing here. But if you were to run this code here, you can see that, again, we've written out a file called kpoints, and if we print the contents of that file, it looks like this. It's a VASP kpoints configuration setting. So again, so far nothing fancy, everything is just largely manual. And the last thing that I'll show is the POTCAR file being written manually. Here you do have to give the symbols that are being used for the POTCAR, and these symbols need to be in the same order as the POTCAR. If you use the automatic generation, which I'll tell you about later, you don't have to worry about this. All of it's taken care of for you. But if you're doing things manually, you do have to make sure that these are in the same order. And then if you initialize the POTCAR object with these symbols and the functional, and again, that chooses which POTCAR directory you're using, it will write out the POTCAR file. And again, once again, you can notice that this symbol here, sodium PV, corresponds to this symbol here. All right, so now that we've talked about writing VASP input files manually, let's talk a little bit about how to automatically write VASP input files, because that is probably the primary mode that most people who use pymatgen to use VASP files use it in. So a VASP input set is basically a recipe to create the appropriate set of input parameters, so all 4 files in CAR, kpoints, POTCAR, and POTCAR, based on a crystal structure and the intended calculation type. So there are many different VASP input sets, and we'll talk about them in the next slide. And so you can choose the appropriate input set for your calculation type. And then if you give the structure to the input set, it will automatically generate all 4 input files for you. And then if you were to give different structures to the input set, then you can actually generate, different directories with files for each structure. So this makes it very easy to run high throughput calculations, especially because these input sets will try their best to adapt the settings appropriately for each structure. So let's briefly talk about the types of VASP input sets that are in pymatgen. Some of the major ones are called MP relax set. So this one does a structure optimization to optimize the lattice parameters as well as the atomic positions of your crystal. The MP static set is largely used for high quality energy calculations as well as to get a good charge density. And then the non-self-consistent field calculations are typically used for band structure or density of states plots. And then finally, this MVL slab set is typically used for surface calculations. Now, there are many different other types of VASP input sets. In fact, if you were to look at pymatgen.io.vasp.sets, what you would find is, maybe a couple of dozen or so different input sets that are intended for different purposes. And there's documentation for each of these in the header of the class. Now, one thing to know is that the prefixes of these input sets have meanings. So MP means materials project settings, and these are the ones that are mostly advised for general use when available. MVL stands for Materials Virtual Lab, and that means this has been calibrated by the research group of Shui-Ping Ong that maintains pymatgen. And then MIT are Massachusetts Institute of Technology, and these are much older input sets that we used back even before pymatgen was created for a particular battery screening project. And these are typically older and less precise settings, so I would not prefer these for the most part. All right, so let's take a quick look and start using some of these input sets. We'll look at MP relax set, the scan relax set, as well as the static set. Okay, so beginning with the MP relax set. The first thing we need to do is, of course, import the VASP input set. And then once we create the VASP input set, we need to initialize it with the structure that we intend to create inputs for. So this is, again, that sodium chloride structure that we created before. But once we give it the structure, we don't really have to tell it in-car tags or k-point densities or anything that we want. We can just call the write input method, and that will already just create all 4 input files. And in the directory that we are running this in, you will see all 4 of these input files being written out for sodium chloride. And if we print out those outputs, you'll see that it tried its best to choose an appropriate K-point density. It automatically prints the POTCAR, and it automatically chooses which POTCARs to use for this material. Now, as I mentioned, there are different input sets for different types of calculations. And in particular, if we want to run a structure optimization with the scan functional, they've calibrated slightly different settings for doing this in the materials project. And so we can initialize the same structure with the scan relaxation set, and then also add one of the optional parameters of this object, which is called the van der Waals correction. And so here we've specified the van der Waals correction to be added as well. And so if you were to write the VASP inputs using this other input set for the same structure, we would get slightly different results. So you can see, for example, there's this meta GGA tag with R2 scan on it. That's because we're using the scan relax set. And then we'll also have van der Waals corrections in here as well, like this LUsed van der Waals set to true because we set this van der Waals tag. All right, so the final input set that we'll look at is the MP static set. And just like all the other input sets, we can initialize it with just the crystal structure that we want to create inputs for. And we can, of course, switch out this crystal structure for other structures and then do this in high throughput. But if we write the inputs using this other input set, and I'm just going to print out 2 of these input files here, we can see that the K-point density is actually a bit higher. I think it was 444 for the relaxation set. And then also we have tags like NSW0, which turns off the structure optimization. So even though it's the same structure, because we gave it a different intention, like this time we want to do a static calculation, we get different settings that have been written out to the various files. Now, in case you've been silently judging some of these settings, like you felt like the K-point density was not high enough or something else, just know that every VASP input set does its best to give sensible settings, and it's usually trying to balance some combination of accuracy and precision, calculation time, and then also convergence rate. So the input set tries its best to kind of balance those things, but there are certainly times when it will give you results that you don't necessarily want or that you want to override some settings of. So every single input set allows you to override whatever settings you want to change. And so we'll just use an example right here of the MP static set and show how could we increase the energy cutoffs and give even a higher K-point density if we wanted to. So the way to do that is to just define 2 dictionaries, one for the in-car settings that we want to update. So here we want to update the energy cutoff to 700. Another one for the K-point settings we want to update. So let's say we want to have a K-point setting such that we have 1,000 K-points per inverse angstrom in reciprocal space. So this is not always the same K-point density for every material. It will try to have the same density of K-points in the reciprocal space. So basically, smaller real space materials, it will have more K-points. Larger real space materials, which have smaller reciprocal space volumes, will have less K-points. Okay, so if we want to override these 2 different parameters, we can again instantiate the MP static set, but now with the user in-car settings set to our in-car settings and the user K-point settings set to our user K-point settings. And pymatgen will make sure to use your user settings if you've submitted them. So here we can see that our energy cutoff is now 700 because we've said it should be 700. And now we've actually have a much higher K-point mesh of 11 by 11 by 11. Remember, it used to be 5 by 5 by 5. And this should be a K-point density that gives you 1,000 K-points per inverse angstrom in reciprocal space. Okay, so the last way that I want to talk about for using VASP input sets is to use a previous calculation as the basis for a new calculation. Because often one of the things that we want to do is to inherit settings from a previous job. Let's say you already ran a structure optimization in VASP with some custom settings that you like and custom, van der Waals corrections and things like that. And you want to run a static run using the MP static set, but you want to basically inherit most of the settings from your previous run and just overload the settings that are needed to make it a static run. So pymatgen makes it possible to instantiate VASP input sets from a previous directory. So what this will do is it will actually read the settings from a completed run. So this was, contains input and output files. And then it will inherit most of the settings from the previous run, but it will overwrite other settings in order to meet the demands of the user. So if here you want a static energy calculation, it's going to make sure to turn NSW to 0 regardless of what you had in the previous calculation. So let me just show you how that works first, and then we'll talk a little bit more about the internals, because the internals are confusing, whereas the usage is simple. So let's talk about the usage first. All right, so if you want to instantiate a calculation from a previous directory, you can, instead of giving the input set a structure like we normally do, we can give it a previous calculation directory. And this directory should contain output files. So if I look here in files and then the HSC relax output, I've removed, I think, most of the output files, but we've kept the vasprun, the OUTCAR, and the CONTCAR, which are the ones that are really necessary for this previous directory to work. Okay, so now if we write the input sets from this previous directory, we can see that it will have read the structure from the CONTCAR of the previous directory. So you can see that, this lattice parameter is 3.329. If you look at the CONTCAR here, you have 3.329 as the lattice parameter. So it's read the structure from the previous directory. It has also inherited some of the INCAR tags from the previous directory. This is actually a hybrid functional run. So it has tags like HF screen and precision FOC, and also other LHF calc equals true. It has all these tags that are associated with hybrid calculations that are not in the typical MP static set. So it has retained all those previous user settings for hybrid calculations, while also adding other tags like NSW equals 0 that are needed to do a static run. Okay, so finally let's talk about where do these rules come from in VaspInputSets, because obviously it seems like magic that you just give it a crystal structure and it just comes up with the correct density functional theory settings to run that crystal structure in with VASP. And obviously those rules are coming from somewhere. So let me just try my best to walk you through at least the beginnings of where to look for when you are looking for where these rules are coming from. Now the first place to look is the config dict, and this is typically a YAML file containing hard-coded settings. So let me show you really quickly for MP relax set in particular. So MP relax set, this is one of the VaspInputSets that we use, has a config dictionary called MP relax set, and that is in pymatgen.io.vasp. And this YAML file will tell you the basic settings that are being used, or the default settings that are being used when we create input files with the relax set input set. So these are the default INCAR settings, and you can see that by default these relaxation settings do use LDA plus U on certain elements. In particular, the U values that are used on different elements are specified here. And the way that this works is that these transition metals, when paired with this ion, have this U, and then these transition metals, when paired with this anion, have this other U. Similarly, you can see the default POTCARs that are being used, and as well as the K-point densities that are being used for this sorts of calculation. So really the basis for every single one of these input sets is a dictionary containing these configuration parameters. Now, layered on top of those settings are, as we just talked about, the INCAR settings from a previous calculation. Because if you've specified the from previous INCAR tag, it will overwrite many of the settings that are in the configuration dictionary with what was in your previous calculation, so that you can properly inherit the settings from your previous calculation into your new calculation. So start with the configuration dictionary. If you call the from previous calculation function to get the settings from the previous INCAR, but then on top of that, we also do other things as well, because many of the settings are determined automatically depending on the crystal structure, and they're not just static settings. So the VaspInputSet.INCAR has some of these rules. There's also a variable called auto updates that has some of these other rules. So let me show you where some of these are. So in the code, let me just show you the parent class of these input sets called VaspInputSet. And VaspInputSet has an INCAR function, which is the thing that returns the INCAR object when you give it a structure. And you can see that there are certain keys, like the magnetic moments, which we'll get into in a second, that are being set based on a series of rules rather than being set as a static tag. Similarly, you can look at things like EDIF and EDIFG. If you've set the energy difference to be per atom, it will automatically calculate that depending on the number of sites in the structure. It will automatically set the Lmax mix tag depending on whether you have D or F electrons. So if you have D electrons, it's going to set it to 4. If you have F electrons, it's going to set it to 6, etc., etc. So some of these tags are being set automatically, and they're going to override the things that are in the config dict or the previous in-car. And then similarly, there's this like auto updates tag with things like n up down that will also be set automatically. All right, following the auto updates is a field called in-car updates, which largely supersedes all the stuff that is in the higher levels. And so this is often used to set up inheritance between input sets. So for example, if you look at the MP static set, here there's something interesting, which is that the configuration file of the static set is actually the same configuration file as a relaxation set. So really the base settings of the static set and the input and the relaxation set are the same. But what happens is that this in-car updates gets called on top of the configuration file. So the in-car updates gets called later. So the in-car updates is going to override a lot of the parameters that were in the configuration dictionary. So here you can see that it's going to set the number of ionic steps to 0. It's going to set the smearing to the tetrahedral method, as well as overwrite several other parameters intended for static calculations. And if you were to initialize the MP static set with like L epsilon set to true, then it's going to update the in-car settings so that you do a static dielectric constant calculation as well. By the way, if this looks weird, it's because MP static set is a data class, and you can look up more about data classes, but they basically just make the initialization of these parameters a little bit neater. Okay, finally, user in-car settings. This, as we talked about, are the settings that the user has decided to specify manually, and that is, of course, the highest priority. So no matter what happened in the previous layers, if you say that, a certain in-car tag needs to be a certain way, that will be respected. Let's now shift to looking at the VASP outputs. So once we've created these input files, we can of course run VASP and then perform the simulation, and then we'll have a series of output files that contain all the calculated information. Some of the output files are the CONTCAR file, the vasprun.xml, the OUTCAR, POTCAR, etc. And the way that pymatgen typically handles this is that there is a mapping between each output file and then an object that represents that output file. And that object is in charge of parsing the information in that output file, as well as making different types of information available as attributes to the class. So let's begin by just parsing some output files. The one exception, by the way, to this object to file one-to-one rule is the CONTCAR file. So I'll show off that one first. So to parse the CONTCAR file, we just use the normal structure object and call from file, and then we can parse a CONTCAR file. Okay, the next output file to look at is the OSZICAR. So this contains all the electronic and ionic steps, as well as the final energies of your calculation. Here, there is a dedicated pymatgen object that will parse an OSZICAR file. And so if you just give it the path of your OSZICAR, this will parse the file. And then this object here will have certain attributes that you can access. For example, ionic steps will be a list of ionic steps, and each ionic step in the list will be like a dictionary of information. So let's just go ahead and run this. And, this length of ionic steps will be 1 because this particular OSZICAR file just has one relaxation in it. The final step is going to be a dictionary. So if you look at the list of ionic steps and get the last element of that list, you will get a dictionary that contains things like the free energy and the change in energy and the magnetization. And so you can print out, let's say, the final step and then the E0 or E0 output of it, and that will print out the final energy for you. You can also get access to the electronic steps, and then the electronic steps is like a sub-dictionary or a sub-list within the ionic steps. So you can iterate across all the ionic steps and across all the electronic steps within each ionic step, and then print out, for example, the convergence path of this particular calculation. And this could be used, for example, to plot a convergence graph or just examine the convergence behavior of your material. Next, let's look at the OUTCAR file. So this is, of course, one of the main output files of VASP that contains a lot of information. Again, there's a one-to-one mapping between an object and the file itself. And once you've created the OUTCAR object, you'll have access to things like the energy and the run stats of your material. And these will be either floats or, let's say, dictionaries in the case of run stats, where you can easily access without having to write grep commands or anything like that, all the information about how the job was run and how long it took and all of that information. Now, of course, there's a lot more than that in the OUTCAR. And one thing to know is that sometimes you have to call a separate read function to get access to those properties. For example, reading the dielectric function can sometimes take a long time. And so this is an optics calculation, so it does contain a dielectric function calculation in it, but by default, it's not read. So before you read the dielectric tensor function, you have to call this read function. Now, side note, I don't know why pymatgen doesn't just lazily call the read frequency dielectric function for you whenever you call this attribute. I feel like I discussed it with Shui at some point. I don't know why we decided not to do it, whether it was time or there was like an actual reason not to do it. But anyway, you do have to like today call the read function first. Okay, so once we've called that function, we have access to the dielectric tensor, and you can see, for example, that we've parsed as easily as like a data dictionary or as a pandas data frame, all the dielectric data. And I'm only showing the first few rows of this dielectric function, but this of course has, you know, many, many rows of different energies and dielectric tensor components. One thing to realize is that because this is a dielectric function, this is a complex number inside each of these tensor components. And so you do have to call like the real or imaginary attribute of them. I'll actually just show that right now. So if you want to plot this dielectric function, we can take the data and get the energy column of the data. We can also get the real part to get the real part of the dielectric function plotted, and the imaginary part to get the imaginary part of the dielectric function plotted. So if we run this, you will see a plot of the real part of the dielectric function as well as the imaginary part of the dielectric function. Okay, so let's talk about one more output file. This is the vasprun.xml file. And now I know a lot of people turn off writing the vasprun.xml file when they run calculations to save space, like disk space. But pymatgen is really, you know, designed to handle the vasprun.xml file. So if you are using pymatgen, I highly recommend that you keep your vasprun.xml files around. Here I'm going to parse a vasprun.xml file from a hybrid relaxation run, and you can see we can do basic analysis like at the energies and the structures, but there's actually a lot more information that you can get from a vasprun.xml file. Let's try a more complicated example. So here we're going to try and parse the entire band structure and density of states from two different vasprun.xml files. We're going to get the band structure from a hybrid calculation that it's in line mode k-points. We're going to get the density of states from a vasprun.xml file that has a uniform, you know, high density k-point mesh. And then to get the band structure, we just have to call the getBandStructure function on our VASPRun object. And then once we have that band structure object that contains all the information about our band structure, it also contains analysis functions like getting the band gap, getting the direct band gap, etc. Similarly, to get the entire density of states information from a VASPRun, you just call the complete DOS attribute of the VASPRun object. So then once you have this band structure object and DOS object, which contains all the information that is in the vasprun.xml file, you can import one of these plotter objects in pymatgen and plot them. So let's just do all of this really quickly. So you can see that pymatgen has parsed the vasprun.xml file. It has printed out information about the band gap, and then it will also tell you if you want, you know, because this is an indirect band gap, it will tell you what is this the smallest direct band gap, and that can be, you know, important for absorption and other properties. Now, you can see also how easily we were able to create a plot of the band structure given these two vasprun.xml files. With just a few lines of code, we were able to get a nice looking plot. And this is actually not a complete, you know, demonstration of what these plots can do. If you have a more complicated structure with multiple elements and multiple types of orbitals, you can project elements and orbitals in the DOS, I think maybe even in the band structure as well. So that's maybe will be something that I demonstrate in like a later tutorial. But for now, we're just going to show off, you know, making the band structure plots and parsing the band structure information very quickly from the vasprun.xml file. Okay, so that's it for today's tutorial. We went over how to create VaspInputSets with VASP. We also talked about how we can very easily parse all the output information that's in VASP. That's typically very difficult to, you know, write custom scripts, etc., to get the information you need. pymatgen already has built-in parsers that allow you to get these objects that have certain attributes that you can access and then get the information that you need from your simulations. So that's it for today's tutorial. Hopefully I will see you in the next one.